Hello everyone, my name is Ashish Mehta and I am a marketing engineer.
My name is Leon and I'm an application engineer.
We both cover national instruments for Southeast Asia, as known as ASEAN. So in this presentation, we will be discussing FPGA technology, the use cases, and how you can take advantage of this technology through LabVIEW. So let's talk about embedded systems challenges. Now Leon, what do you think are some of the main challenges for embedded systems design?
Well, there are a few. Here are some of the quite significant ones. For example, high-speed I/O and analysis, system uptime and reliability, high-speed or deterministic control.
That is spot on, Leon. So a good example for high-speed I/O and analysis would be oil well pump monitoring. Now these systems require high-speed analysis to catch momentary spikes in pressure and vibration. Another example is system uptime and reliability, which you mentioned earlier. You may be controlling a plant such as a biorefinery, which requires fail-safe control systems throughout. Finally, the other aspect you mentioned, which is system that requires high speed and high deterministic control, a good example would be an extremely large telescope such as ELT. These devices use nanometric positioning actuators and therefore require very precise control. Now you could attempt to solve these applications with a processor-only solution, but here you might encounter some shortfalls. Here's a quick overview of a processor-based approach. As you all know, a processor-based approach is extremely flexible and has an extensive layer of driver-level API that's usually needed to build complex applications. However, when you are looking to do a specific task that requires extremely high performance and reliability, for example, critical control for laser eye surgery, the task will have to depend on an operating system and another layer of driver API from the hardware I/O to the calculation. So that's pretty long path for the inputs to get to the calculation and the outputs to react to a stimulus. Now the layers of software that exist between the hardware and your calculation add overhead and also may crash in one of the layers. So one way to go about it would be having a very ideal scenario of just having a specific task that's implemented within hardware. And that's for something which is high performance and requires high reliability. And this bypasses all the unreliable software layers. Now by doing this, we have the highest reliability and response time and in the order of nanoseconds. This is what FPGA enables us to do. So hopefully I've given you a good perspective of why FPGAs are even used. So let's just take a track back and look into overall engineering challenges that we face today. So hey Leon, do you think engineering is getting more complex?
Yes, of course. Our smartphones itself has so many different applications. Now I actually depends on it to go to places every day.
That's true. As engineers, we have to do more with less. We have to integrate multiple systems that's getting more complex. As Leon mentioned itself, smartphones.
Yeah.
We depend on smartphones a lot, especially to get you to places, to even be able to tell you what to do next in terms of tasks. 8 years ago, my expectations of a phone was just to make a call or even receive a call, maybe even send a text message. But right now, people's expectations have really increased as technology has advanced with also innovation. So at National Instruments, we have a mission. The mission is to equip engineers and scientists with tools that accelerate productivity, innovation, and discovery. So essentially, we believe in creating tools that help every engineer, scientist out there to be able to solve very complex problems. At National Instruments, we create tools for a platform-based approach by providing graphical software with modular hardware to build measurement and control systems faster. Fundamentally, we provide software and hardware platform tools to measure and control the world around us. On the hardware side, We provide high performance to low cost modular measurement and control hardware with thousands of configurations available to mix and match for custom analog, digital, machine vision, control, and other needs from lab to industrial form factors. We also provide highly integrated systems including PXI and CompactRIO, from desktop computing to real-time and embedded systems, leveraging our modular measurement and control hardware in complete customizable systems. All of the hardware is defined by the software known as NI LabVIEW, enabling users to design, prototype, and deploy custom systems that acquire, control, analyze, and present the real-world data. Now, we've talked about integrating software and hardware seamlessly. To be able to do this, we have a specific vision called Graphical System Design. This is a platform-based approach for measurement and control. Now, we believe LabVIEW is the key system design software that graphically simplifies the complexity of integrating all these elements in a single open environment. It scales across different deployment targets with the same architecture so that you can choose the instance of the platform that best fits your specific application. But if your needs change, you can easily migrate to other options such as ruggedized, high performance, or even higher channel count. Now, in terms of simplicity, this is the kind of simplicity delivered by the graphical system design approach. Now, when we talk about simplicity, let's have a look at the graphical system design approach that can save you months of development time and changes the dynamic of your development needs. As you can see, instead of programming lines and lines of code, we can simply program all this using just a few graphical nodes. So not only are we simplifying software, we are simplifying hardware by integrating modular and commercial technology into a small footprint called PXI. Now all this is configured and programmed using our graphical system design approach with LabVIEW. When developing more complex embedded systems, rather than building everything from scratch using components or integrating various tool chains, the NI platform provides an integrated system to get you started for custom advanced measurement and advanced control in the same system. Whether you are designing a test system or a control system or one that needs to do both, you have an integrated software and hardware approach to develop systems faster. Now, we talked about this graphical system design approach where the heart is the LabVIEW software and how easily it can integrate with various hardware platforms. Now, LabVIEW was first introduced in 1986 when LabVIEW revolutionized the way engineers and scientists develop systems in an intuitive graphical way. LabVIEW is a flexible, open software that can help scale from small to large and complex systems. On the left, as you can see, we have a LEGO Mindstorms robot, which is programmed using a simplified version of LabVIEW, allowing kids between 5 to 18 years old to develop custom robots. That's pretty cool. At the other end of the spectrum, we see LabVIEW being used to control the launch of the SpaceX Dragon spacecraft. And that's pretty complex and pretty hardcore actually. Now, let's just talk about why we're here today. That's FPGA technology. So I guess the first question would be, what is FPGA? So FPGAs are field-programmable gate arrays, essentially a silicon chip with unconnected logic gates. You can define the functionality of the FPGA by using software to configure the FPGA gates. There is no operating system needed. So essentially, your logic executes only in hardware. This is going to give you extreme high reliability in terms of application development. Also, because the FPGA has I/O pins directly connected to the FPGA fabric where your logic resides, you can perform inline signal processing with minimal latency and very high-speed closed-loop control. Specifically, you can obtain around a 200 kHz loop rate for motion control or analog PID. So now that you know what an FPGA is, let's look into the challenges of developing. So Leon, what are the main challenges of developing for an FPGA-based embedded system?
Well, normally we will have to use different multiple tools in order to develop for various targets.
Exactly, you'd have to use multiple software tools to develop for all the different targets that's involved. Now that's absolutely spot on, Leon. And with this day and age of multi-core processors, designing for parallel processing can get very complex. All this will require a long learning curve, and a specialist, and actually multiple specialists, will be needed for each tool used. Now this is not the best situation because this will increase cost and time to market. That being said, let's look into the NI approach. Now the NI approach to solving these applications is to incorporate both an FPGA and a processor into a single device, where the FPGA is directly connected to Modular I/O. This is what we call the LabVIEW RIO architecture. Now RIO stands for reconfigurable input-output. Then the LabVIEW graphical programming environment is used to design this entire system, and it includes built-in functions for handling I/O and bus interfaces, which provides you with maximum power and flexibility.
So Ashish, we are using one single graphical programming environment, NI LabVIEW, to program the processor, FPGA, and all the I/Os?
Yes, Leon, that's exactly right. We're using LabVIEW to program for processor, FPGA, and all the I/O. So how would you map your control or test application to this kind of architecture? So let's have a look at high-speed control application. So if you like to design a high-speed control application, you will want to offload your most critical tasks to the FPGA. In this case, our acquisition and control loop, in addition to a watchdog timer to detect and recover from any software failures. The majority of your application may live in the processor, including tasks such as system monitoring, message handling, a sequencer, or the data logging engine. Now finally, we can communicate from our embedded processor to an HMI using network communication mechanisms built into LabVIEW. We can also take a look into a high-throughput test application. High-throughput test applications are typically acquiring data at extremely high rates and performing high-speed analysis upon a trigger condition. Rather than sending large waveforms and data sets to a CPU for processing, we can perform all our processing and analysis in hardware and only send the measurement results from the FPGA. This greatly reduces the amount of traffic within the communication bus and frees up the CPU to perform other tasks. Also, since the FPGA can run faster than the rate at which data is acquired, we can guarantee that every sample is seen and processed. And finally, the FPGA can also be used to control the DUT, which allows us to design this entire system using only one device. So LabVIEW not only enables you to design FPGA applications, but you can program your entire embedded or test system, including communication to and from HMIs, NI or third-party embedded systems, enterprise storage solutions, and the cloud, all using LabVIEW Graphical System Design. Now, LabVIEW FPGA allows users to leverage graphical system design for FPGA-based applications. Having the option to program graphically with the LabVIEW FPGA module allows users to incorporate third-party IP from Xilinx, leverage some of the latest technologies such as HLS, known as high-level synthesis, using the LabVIEW FPGA IP block product, and integrate third-party VHDL, all within a single development environment. The software that you design using these tools can then be deployed to various NI RIO hardware targets depending on the performance, form factor, power, and I/O requirements. So as you can see, there's a wide array of options for you to choose the right LabVIEW RIO hardware target that is ideal for your application. All of these hardware targets leverage the LabVIEW RIO architecture as we talked about before. Now the LabVIEW RIO architecture breaks out into different hardware products which fall into three categories: CompactRIO and SBRIO, expansion I/O if you are looking at creating distributed applications, and high performance. All of these products come in many different variants which range in performance, including I/O, CPU speed, memory, and FPGA size. So here's a quick excerpt from the CTO of Xilinx. So he mentioned that high-level language is required to make FPGAs accessible to all engineers and scientists out there. Specifically mentioned that LabVIEW is the ideal tool to program FPGAs because of its ability to enable domain experts to program an FPGA device. Now, here's a pictorial representation of how LabVIEW can be mapped to FPGAs. One of the main benefits of using LabVIEW to target FPGAs is that the graphical dataflow nature of LabVIEW is well suited for implementing and visualizing the type of parallel operations that can be implemented in FPGAs. For example, these two tasks shown here are each implemented in the FPGA with their own dedicated resources, which is what is described as truly parallel. As we add more loops or tasks to this system, the performance of the tasks that are already implemented will not be affected. So just bear in mind that this particular example that we have here, which shows the mapping on the FPGA and the graphical aspect, is just a pictorial overview to show you the concept of parallelism. So it's not exactly how it will be mapped up in FPGA. That will really depend on the compile process, which we will talk about later on.
So I'd like to actually introduce you about this LabVIEW FPGA, which enables user to target high performance FPGAs with the same graphical development environment that's used for desktop and real-time applications. You will write FPGA codes which is similar to LabVIEW code written for a PC, but with a more limited platelets and some different program structures due to the different platform itself. You will also have this block diagram where you begin to write your code, and your front panel, which is used for development and debugging purpose. When your system is developed and deployed, the front panel will be used to communicate data between your FPGA VI and your host VI, which is running on the adjacent processor. Okay, so before we start off this demo, I would like to navigate you through the three windows which you see in front of you. Okay, on your left will be the Project Explorer, which is effectively known as your system configuration. It will indicate the applications, target, deployment which you are using. There will also be an indication of I/O modules that will use in the program. This is presented as the blue icons that indicates, as you can see, analog input module. So for each application, which is known as a virtual instruments, commonly known as VIs, will also be represented as a .vi file here. As you can see inside the window, is further indicated as read analyze sine wave.vi, for example. Okay, each VI will have a front panel, which is shown as the middle window. It is the main user interface for your user to input and read the analyzed data from your application. And the third window on the right, which is your block diagram, this is where you input your codes and define the functions of your applications. In the demo later, you will effectively using these three windows in achieving your first FPGA program. Next, we would like to introduce you the hardware that's involved in this demo.
Right, so it's fantastic. So essentially over here we have a whole integrated development environment where you can see all your targets, such as hardware targets and also the software that's running underneath the target, all within the project. So this is amazing. Thank you very much, Leon. So let's have a look at the demo.
Yes. Here's a picture of the hardware that we'll be using for this demo. On your left, it is the CompactRIO 9076, which is the integrated real-time controller with the FPGA at the backplane of the chassis. These are the modules that we are connected to the system. We have the NI 9205, the 32-channel analog input module, which we will be using it for measuring voltages. Next is the NI 9263. We will be using this 4-channel analog output module for generating voltages. Next will be the digital modules, which is the NI 9421, the 8-channel digital input syncing module. The last module will be the NI 9474, the 8-channel digital output sourcing module. Lastly, on the right will be the PS15, which is the 24-volt power supply that we use to power up the whole system. Right, so now we have talked about the hardware and as well as the software windows. So let us start to discuss on how do we actually develop the FPGA from here. And from here on, I will just show you step by step in creating the program from scratch.
Amazing. Everyone, get ready to be excited.
Here we're going to start in writing our FPGA code itself. So what you will see first when starting on this LabVIEW 2013, you will come to this welcome page. In the welcome page itself, you can see that we have a few options. Either you can open up the existing project or you can create a new project. So LabVIEW 2013 itself also enables you to have a template, which is to start off the project as given as a template where you can just start to write the coding in. Okay, this is all the options and all the selections you can do. But for today, we are doing a new blank project so that you can have the appreciation to start everything from fresh. Okay, so this is the project that actually I started. First of all, I would like to do a save. Okay, I will save it as my FPGA program as the name of my project. Okay, you can see that now the name has been changed to my FPGA program. In this project explorer is, as I've last introduced to you, that you can do all the compilation and all the referencing to all the required programs and hardware in this chapter. So right now I'm going to add in the targeted devices to my project. So you go to new and you go to target and devices. Okay, as there is my hardware has been connected to my development PC, you can use these options of existing target or devices. LabVIEW will able to auto discover what was the hardware being connected to it. So as the hardware that I'll be using will be a real-time CompactRIO. The moment I click on it, it will do an auto detection or what kind of controller it is. As you can see, this is the serial 9076 with the serial number. So I will just click on it. Okay, when doing this programming, you can do in two types, either towards this scan interface, which is a very cool features. It will auto detect and you can start using all the modules and IOs immediately by using the scan. However, if you are using the FPGA, you need to do some programming in order to use these IOs. Okay, for the purpose of this demo, that we will concentrate in LabVIEW FPGA, therefore I will choose the LabVIEW FPGA interface.
So the scan interface is essentially a simpler way to access the IOs without programming or programming the FPGA at all.
Mm-hmm.
Okay, so in this case, we're just doing the FPGA programming.
Yes.
Perfect.
Okay, so I just do a continuation, and immediately the program will also discover whatever modules that are connected to the chassis, and with that, all the references to the hardware is complete. You can see that all has been listed out on the modules that I introduced to you earlier on, like this NI9205, 9263, 9421 and 9474. It's all have been auto detected because it has been connected to the chassis. Right now, I like to do some remaining so that it will make it more meaningful when you read through the program itself. So for example, this 9205 will be our analog input module. And for the module 2, which is the NI 9263, will be the analog output module. Okay, module number 3 is our digital input module. Module number 4 will be the digital output module. Okay, with all the required referencing of the hardware is done, okay, we are ready to build our first VI, which is the applications. Okay, we will build our VI we can have selections to build our VI to be on 3 different kinds of aspect. Number 1 is that we can actually build it on my computer, which is the VI will be appearing to run on your desktop itself, which is the development PC. As another words, we call it a host PC. Or we can do it on the real-time interface as another way that you can actually add a VI. And lastly, you can also put this VI under the FPGA mode itself. So for today, we would like to create a VI under the FPGA. So from now on, you can see that we have the front panel and the block diagram. Okay, let me just do a little bit of reorganization by having the Control T to make sure that you can see all the windows under one screen. Okay, let me do a bit of adjustment. So right now we will start to create our application of the VI from here, as you can see from these 3 windows itself. Okay, first of all, I like to generate a certain level of voltage out towards the analog output module. So the first thing that I need to do is to have indication of the control in the front panel so that I can actually control what are the voltage that I'm going to output towards the analog output module. So I will have a right click and we'll go on to the numeric control. Okay, and I will select maybe a vertical pointer slide. So in this case, you are able to see what is the required values that you have selected that you want to control on your analog output. Okay, you can do some editing in terms of changing the shape of this slider so that to make it much more presentable and visible to your user. And next, I would like to control the analog output, which is the channel 0. Okay, so from there I will just choose and drag it into our block diagram. Now you see that on this block diagram, which is the code, that you have this slide terminal and as well as the output channel. From there I would like to do a connection, and this wire is an indication of the data flow from the control of my front panel slider into the analog output module. And this will enables me to define what is the voltage I want to output from this analog output module. Okay, so right now I would like to develop this into a more meaningful demonstration. Okay, I will develop alarming applications. So this application requires me to output a certain value of analog voltage, and I will use the analog input module to measure the output voltage. If the measured voltage is over the presetting threshold, it will give a digital signal of an alarm. Okay, so right now let us go on to build this analog input signal. Okay, so I will go on to the analog input module. I will just use channel 0. I will just drag it into the block diagram, and with that I will be having my measuring voltage terminal being here. Okay, I would like to have an indicator to show what is the measured voltage. So I will go on to the output terminal of this analog input module and create an indicator. So this shows the indicator of the measured voltage. Okay, Okay, I would like to rename this as measured voltage. Okay, and as the default display is in 23 digits, I want to keep things simple because my output voltage is just from 0 to 10. I like to reduce this digit to 3 and also to hide the trailing 0 to keep the measurements reading simple. Okay, I would also like to rename my slide now as output voltage. Okay, so with that, I have set up a basic structure in measuring the output voltage using the analog input module. And the next step I'm going to do is to set up my threshold. So with that, I will go on to the front panel, adding under numeric, and put in a numeric control. And I would like to rename it as, this is my threshold. Okay. Okay, right now I can see that is the data type that is being used is in the integer of 16. Okay, for this particular threshold, I would like to make it consistent with the analog input module, which is the fixed data point, and I'm going to change this representation to a fixed point. Okay, if you use the same comparison of the data type, it will make this program to be running much more efficient and be optimized. So that's why I like to change this representation. And this whole measured voltage will be compared with this threshold voltage. So in this case, I will do a little bit of comparison. So I will have the right click and go on to comparison and choose greater. So this will define that if the measured voltage is greater than my threshold, you will generate a true signal from here. So a true signal towards my alarm. Next, I will add in an alarm icon. So I will go on to the Boolean platelet, and under the Boolean platelet, I will have this round LED as an indication of the alarm. As the default size was a little bit small, I like to increase the size to make it much more visible, and as well as to rename it as the alarm. And for that, I will connect the output of this comparison towards the alarm. So from my soft front panel, you can see that there is an alarm, my output voltage, the measure voltage, and as well as the threshold. I would like to relate this program towards my hardware. So right now I'm going to put in the physical side of my LED, which is connected to channel 5 of the output digital module. So I'm going to click on and put as a referencing. So if there is an alarm happening, I will be able to show it on the physical side of my module. Okay, and the program will not be complete if you, let's say you're running for it as once. I want to have the consistency of running this program to keep on running until I stop running the program. So I would like to add in additional structure to this program itself. So I will go on to right click it and add a structure of the while loop. Okay. By adding on the while loop is that the condition will be running until the condition is met before we exit the program itself. So in this case, I would like to have certain control over this program by having a stop button. So I will have the right click on this stop and create a control. So at the same time, on my front panel, it will appear the stop button itself. I like to do a little bit of renaming in terms of to give me as stop running, means you stop the program from running. Okay, with that, my program is almost complete. I would like to add additional features because on my digital modules there is an output switch, which is what I use to consider as an external stop button to this program. So I want to make it more meaningful in terms of adding it to the software interface. So right now I'm going to add in this external stop button to this program itself. Okay, so my program, my switch was added inside this digital input channel 0, so I will just drag it in. Okay, so I would like to make this program to able to stop using two conditions. It's either I press the stop button on the stop running, or I use the switch that is connected to the hardware to stop this program. So in this scenario, I want to add in an OR gate to indicate that I can stop this program using either way. Okay, so I would like to do a bit of a rewiring. So on this connection, I will able to stop the program by putting a high towards a digital input channel 0, or I can generate a true from the front panel here in order to stop the program. Okay, I would also like to add in an additional terminal which is under the digital output module to serve as a simulated power supply to my switch itself. So I will add a true constant here to indicate it's always generate a high. So with that, my program is completed. Okay, let us have a final check on various pointers that I actually created. Number one, I will use this slider, which is indication of the output voltage, to decide what is the output voltage I want to generate out from the analog output module. And this was hardwired and connected to this analog input module channel 0, which is I will have the indication of the measured voltage here, and the measured voltage will have the brief comparison between my threshold, and if the measured voltage is over the threshold, it will generate a true signal towards the alarm, which is on my soft front panel, and also the LED on connecting to my digital output module. Okay, the additional features is that I can stop this program from running in using the soft front panel stop button or the switch that was connected to my digital input module channel 0. Okay, so with that, we are ready to run our program.
Okay, so basically the whatever's coded in the block diagram will be only running the FPGA. Whatever comes up in the front panel is just a viewable aspect that happens on your PC.
Yes.
Because there's no operating system on the FPGA, it's running all on hardware.
Correct.
So only the logic would be running on the FPGA.
Yes, it is.
Perfect. That's interesting.
Yeah. Okay, so with that, I would like to start our compilation process by clicking the run button on the top left corner of the front panel or the block diagram. So I will just click it. So with that, it will start to generate the intermediate files. Okay, it will generate and create these FPGA codings into the Xiaoling tool change.
So I believe later on you'll be talking about this.
Yes, that will be further illustrate inside my slides later. And this is the compilation status window itself, and we will do all the relevant checks and analysis for you. Okay, right now I'm going to show you that this is the project that was completed earlier on. It is something that is similar to what we had just created earlier on, it has been compiled and is ready to run. I also added certain few more notes to indicate what this program is all about, once again as a summary. Okay, so right now let's run this program. Okay, so from now you can see that under my analog output, which is the output voltage, that I actually can make a control, and there's a threshold of 3 volt itself, and this is the analog input module is doing the measurement. Okay, it's currently I set at 0, therefore it's always at 0 volt itself. So the moment I increase it to more than 3, the alarm start to light up. Okay, so the system works in terms of when I go above 3, it will start to have a light up. Okay, and this is the basic functionality of this program. And the next feature will be when I press the stop button, you can see that on the top left corner, here is actually to indicate the program is running. The moment I press the stop running button, it will stop running. So now I'm going to do it. You can see that now the program has been stopped running. Okay, this is to have the user interface under the soft front panel. Let us take a look at the hardware side where we actually do the exactly same thing, or what's going to happen on the hardware side. Alright, so let us change the view to whatever hardware that I just set up to synchronize after you have seen this software panel adjustment. Okay, I'd like to bring your attention to orientate you towards my hardware configuration is that the alarm button that was found on this software panel will be indicated by the LEDs over at the second row. You can see that under this bit number 5. Okay, so this LED will light up when whenever there's an alarm. Same goes for the LED here. Okay, both of them will be light up when there's an alarm. Okay, number 2 is that whenever I switch on this external switch, this bit 0 of this 9421 will light up as well to indicate that I have selected the external switch to on. Okay, so this is going to happen. So I'm going to demo to you what is going to happen when there's an alarm. So my output voltage is currently at 2 volt, which is 1 volt below my threshold of 3 volts. So now I'm going to increase. I'd like to bring your attention towards what's happening at the LED side. So you can see that the LED has successfully light up according to generate an alarm. Okay, so I'm moving the slider up and down. You can see that the actions has been complete by lighting up the LED. Okay, so now step number 2 is that I'm going to stop the program. The moment I switch off this light, because this light is actually a toggle switch, currently at off position, the moment I switch it to on, the program will stop running, and at the same time the LED at bit 0 of a 9421 will light up. Okay, this is what's going to happen. Okay, you can see that the LED has light up to indicate that I have input a stop button from the external switch and the program has stopped running. Okay, so we have talked about the LabVIEW FPGA I/O nodes. So let's talk about loops and timings. In the typical desktop applications, you can only achieve timing in milliseconds clock range while using the while loop. In LabVIEW FPGA, you can use the timing functions to execute loops in the milliseconds, microseconds, or ticks of the 40 MHz FPGA clock. For example, in this structure, it relies on the monitoring of the base clock and counting a certain number of ticks before executing the next loop iteration. So these examples that are able to let you achieve a faster range of the executing time. In the LabVIEW FPGA, you can also able to streamline the entire loops into one same clock cycle by using the single cycle time loop instead of using the while loop. This can be used to further optimize the performance of a code in achieving a faster timing. FPGA are great options for implementing high performance IP. Whether it's high-speed control or a custom digital protocol, however, you don't always have to build your IP from the ground up. A lot of times you can look to see what's available and incorporate existing IP into your design. With the product, LabVIEW FPGA includes math and analysis libraries such as metric algebra and PID control. It also includes the access to a wide array of Xilinx Core Gen IP. Xilinx is a world-leading provider of all programmable devices, and we partner with them to incorporate their FPGA and processor technology into our hardware. If you can't find the IP that you need in the product, you can always search for our community online at ni.com/IPNET. Here we have both R&D developed and community developed IP that is ready for your use. In addition to IP that's written in LabVIEW, you can also reuse any HDL code. You may want to consider this if you are having existing IP written in HDL, or if someone on your team is a specialist in HDL. You can import LabVIEW FPGA through the IP integration nodes, similar to calling a DLL in LabVIEW real-time or LabVIEW for the desktop. As we shown earlier in the demo as well, the compilation starts when you click on the Run button, which is to indicate the run the program on your deployment targets. It will first taking your Graphical LabVIEW FPGA code, and then it uses the Xilinx tool change to compile that code into VHDL, which then will be able to convert into a bit file or circuit specifications that will be loaded to your FPGA device. At most of the time will be spent within the Xilinx tool change in the transition optimization, synthesis and bit stream generation phase. Whether you are programming your device in LabVIEW FPGA or VHDL, you will need to go through this process, which takes anywhere from 10 minutes to several hours. The overhead in converting the LabVIEW FPGA code into VHDL is actually very small.
So that's interesting. So basically all this happens in the background. So you don't actually have to worry about performing on any of this because it's all automatic.
Yes, it's actually automatic. Okay.
Fantastic.
Another way that you can kick off the compilation process is that you can create a build specification in your LabVIEW project. Upon doing this, you will have a dialog which gives you the options to compile to your local machine, a compile farm, or a high performance cloud. Depending on the size of your FPGA VI and the amount of time you expect it to take, you can leverage these different options to save time. The highest performance will be obtained using the compile cloud, which offloads your compile process to the high performance Linux server. But if you have concern about uploading your code to the cloud, you can set up your own compile farm in-house. As FPGA are reconfigurable, and so from your host VI, you can load multiple bit files to the FPGA during runtime. You can reference this bit file by a file path from within the host applications. In this way, it enables your application to run on multitasking modes. Okay. Through extractions of hardware complexities, building maps and analysis libraries and tools for integrating HDL code, LabVIEW FPGA maximize your productivity while designing high performance and reliable codes. Whether it is high-speed control, custom protocol, inline signal processing, or custom synchronization, they can be easily created using LabVIEW FPGA. So far for now, I'm done with the FPGA demo. Let us pass this back to Ashish for further illustration of the benefits of the platform-based approach. Ashish?
Thank you very much, Leon. Well, as mentioned earlier, the growing complexity of both embedded and test systems is driving an increased number of our customers to leverage a common platform-based approach. Now, having the flexibility of the off-the-shelf hardware gives you the ability to innovate with confidence without the expense and complexity of a custom design. In addition to the flexibility of this platform, it also combines the ability to implement custom algorithms, high-speed control and processing, and world-class analog and digital I/O into a single system. Now I'd like to talk about a pretty cool engineering story where high precision control and safety and reliability was all required. So traditionally for cataract surgery, a doctor would have to really cut the front layer of the eye to access the affected lens. Now this is actually quite a dangerous process because any mistake here would easily puncture the liquid sac underneath the lens, and that's really bad if that ever happens. So Mike from Optimatica saw a possibility to automate the whole process and make just people's lives and the quality of life in general a lot better. So he didn't really worry about the tools. So what he did was spend most of his time with the domain experts such as doctors out there and surgeons, and he also looked into the experience of the patients. So what he did, he then implemented an automated laser cutting machine that was guided by vision, all using one platform, LabVIEW with FPGA hardware. So this is GSD platform put to full use, especially when this application is now available to everyone around the world, as he sold it to a worldwide company called Abbott Laboratories for $400 million.
Wow.
That's amazing, isn't it?
Yeah, it's amazing.
Well, as we wind down the presentation and then wind down about the introduction, let me give you a few resources to look at. So to learn more about FPGA technology and what NI has to offer, please feel free to check out ni.com/FPGA. Here you can find wonderful information on FPGA fundamentals, benefits of FPGAs, NI FPGA based case studies, and also learn more about tools such as LabVIEW FPGA, LabVIEW based Rio hardware. If you want to start improving your skills in LabVIEW, there's also the LabVIEW Skill Development Plan. So NI offers a sequence of LabVIEW courses and certifications to ensure your success with LabVIEW and gain recognition for your technical expertise. So you have the core LabVIEW, embedded controls and monitoring aspect, and also a high throughput test. So now, if you want more details on the course descriptions and the schedules, please do check out ni.com/training or just call your local representative to find out more about these things. Another great resource is the LabVIEW for CompactRIO Developers Guide. Now, here you can actually refer to multiple forms of architecture and various guides for frameworks. And there's also downloadable example code where you can actually look through this code and start up your application a lot faster. Now, to check this out, you have to actually go to ni.com/CompactRIO Dev Guide. Now, as LabVIEW has been developing since 1986, there's been a lot of different architectures that have been used over and over again. So we've taken all these different architectures that have been proven, have been constantly being used, and put it into LabVIEW itself, allowing our customers to make use and reuse these architectures. So there's a lot of sample projects such as control and monitoring, control for sequencer engine, real-time control and monitoring, and also waveform acquisition and logging sample projects, plus a lot more that already exist within LabVIEW to get you started. So you're not starting from scratch, you're starting from proven architecture. Thank you very much for attending this webcast. I hope you have enjoyed this and got some basic understanding of FPGAs and the LabVIEW FPGA module. So now it's time for feedback. So please share your feedback through a survey using the link as shown in this presentation. We'll also provide the link in the chat window. So 10 lucky winners will get our exclusive gift set. Now the submission deadline will close on the 23rd of May 2014. And the results will be announced via our Facebook page. So it's facebook.com/ASEAN.NI. And the deadline will be on the 5th of June. So thank you very much, and we will be here for the next 10 minutes to answer questions. Have a nice day.